Okay. All right, and so, by going through essentially just a material balance, we're able to come up with our lever rule equations. But we still don't precisely know how to get x1 alpha and x1 beta. In order to do that, what we need to do is go back to the fact and look at the shape of our curve. Go back to the fact that this binary tangent line that we drew indicates that the slopes at each of these 2 points are equal. Okay? And so, that tangent line corresponds to the point where if we took the delta g of mix with respect to dx1 and we looked at it for the alpha phase, this partial derivative would also be equal to dx1 in the beta phase. So this partial derivative, it's just a mathematical way to determine a slope, and we're just saying the slope at x1 alpha is equal to the slope at x1 beta. Okay? Another thing I want to point out is that if we go back to that original x1 composition, x1 naught, we see that it's facing down. Okay? And so what that means, mathematically, is that at x1 naught, delta G mix is concave down. So that means that the second derivative of delta G mix with respect to x1 has to be negative. Okay? All right, so that's what the graph tells us. The graph tells us, what the math has to describe. Okay? All right, and so based on those ideas, what we can do is we can use those criteria to find x1 alpha and x1 beta. Right. And so let's start with our delta G of mix equation, which was just RT summation of xi ln of xi plus that excess Gibbs energy. Right. The tangent line says that the slopes at alpha and beta have to be equal. So what we should do is we should just take the derivative of delta G of mix with respect to x1. Okay? And since we only have 2 species, I could write this out pretty easily. So I'll write it for clarity. Plus 1 minus x1 ln of 1 minus x1. I count my, yep. So we're taking this derivative. If we work it out, we get this equation. Ln of 1 minus x1. So I skipped a couple of steps of algebra. Feel free to work through it yourself. But the equations should simplify down to this. Okay, where here I'm just saying, this is just the derivative of the excess Gibbs energy. So, and we haven't assumed a model yet, so I'm not going to, the actual functional form of this derivative will depend on the model that we choose. All right, so that's the first derivative. But now we also need to account for the part that says that at x1 naught, the delta G mix is concave down. Okay, and so now we need to look at the second derivative. And if we take the second derivative of delta G mix, or just take the first derivative of this, what we get is this equation. Okay? Or if we rearrange it, we could write it like this. And so, based on the fact that in order for phase separation to occur, we need to have this bump in our delta G mixing curve, and that bump needs to be concave down. And so what that tells us is that the second derivative of delta G mix needs to be less than 0. Okay? And so, in order for phase separation to occur in our system, this equation needs to be true. So criteria for phase separation. All right. Or more precisely, if this equation is less than 0, then we have separation. And that critical point that I kept mentioning, the temperature or the composition in which marks a line below or above which phase separation will occur, it would be when we take this equation and set it equal to 0.